X-rays, being electromagnetic radiations, also undergo the phenomenon of diffraction as observed for the visible light. However, unlike visible light, X-rays cannot be diffracted by ordinary optical grating because of their very short wavelengths. In 1912, a German physicist, Max von Laue, suggested the use of a single crystal to produce diffraction of X-rays. Since all the atoms in a single crystal are regularly arranged with interatomic spacing of the order of few angstroms, a single crystal can act as a three-dimensional natural grating for X-rays. In 1912, W.H. Bragg and W.L. Bragg put forward a model which generates the condition for diffraction in a very simple way for X-rays. They pointed that a crystal may be divided into various sets of parallel planes. The directions of diffraction lines can then be counted for if X-rays are considered to be reflected by such a set of parallel atomic planes followed by the constructive interference of the resulting reflected rays. The problem of diffraction of X-rays by the atoms was converted into the problem of reflection of X-rays by the parallel atomic planes. Hence the word diffraction and reflection are mutually interchangeable in Bragg's treatment. Based on these considerations, Bragg derived a simple mathematical relationship which serves as a condition for the Bragg reflection to occur. This condition is known as the Bragg's law. To obtain Bragg's law, consider a set of parallel atomic planes with interplanar spacing d. Let a parallel beam of X-rays of wavelength lambda be incident on these parallel planes at a glancing angle theta. Consider two such rays, ray 1 and ray 2, which strike the first two planes and get partially reflected at the same angle theta in accordance with the Bragg's treatment. The diffraction is the consequence of constructive interference of these reflected rays. The path difference between ray 1 and ray 2 is therefore calculated to be 2d sin theta.
For constructive interference of rays 1 and 2, the path difference must be an integral multiple of wavelength lambda, that is 2d sin theta must be equal to n lambda,
where n is the integer. The equation is called Bragg's law. N represents the order of reflection. For n is equals to 0, we get 0th order reflection which occurs for theta to be 0. That is, the direction is in the direction of the incident beam. The diffraction lines appearing for n is equals to 1, 2 and 3 are called the first, second and the third order diffraction lines respectively. The intensity of the reflected lines decreases with increase in the value of n or theta. The highest possible order is determined by the condition that sin theta cannot exceed unity. Also, since sin theta is less than equals to 1, lambda must be less than equals to d for Bragg's reflection to occur. Taking d approximately to be 10 raised to power minus 10 meter, we obtain lambda less than equals to 10 raised to power minus 10 meter or 1 angstrom. X-rays having wavelength in this range are therefore preferred for analysis of crystal structure.